Yep, so g'day, my name is Brandon, and today I'll be doing my research proposal on this monstrous title called The Optimization of N-Isopropylacrylamide with NN, Methylenebisacrylamide gel dosimeters. We're lazy, so we call them NIPAM and BIS. I'd like to thank my supervisors, Pejman and David from UWA and Murdoch, respectively, for giving me advice and support throughout the whole project. So I really, really appreciate that. There we go. So the main aim of this project is to create a standardized fabrication procedure that optimizes the composition weight ratio between NIPAM and BIS in gel dosimeters that could be used for future research or treatment planning system verification. I'll go through that bit by bit a little bit later on. But the main aim of creating a gel dosimeter is to achieve the following. So it's to achieve the tissue equivalency, dose linearity, low temperature dependency, low dose rate dependency, low dose gradient dependency, high dose sensitivity, and high temporal stability. So in the ideal world, they'll be all achieved. So for a bit of background, so a gel dosimeter is a chemical dosimeter that can measure dose in 3 dimensions, and this is initiated through something called free radical polymerization. So unlike ion chambers, which is the pharma type they've got here and the parallel plate here, that only measures dose in 1 dimension, or film that measures dose in 2 dimensions. Fun fact, both of these are used in TRS 398, if you're wondering. Gel dosimeters can measure dose in 3 dimensions. So this, so as you can see on, in figure 1 here, the more dose there is, the more opaque it becomes. And because you put it in a glass vial, you can use MRI or CT to image it. And it's like, I found it's pretty cool. The main thing about gel dosimeters is that they want to achieve tissue equivalent, which is around 9:1 water to gelatin ratio. So there's a ratio between water and gelatin, which is 9:1. I've got there. So it's mainly 9 parts water, and instead of 10 parts gelatin, we're going to substitute some of the gelatin with some monomers and cross-linkers and some antioxidants. The math doesn't check out, but it's around there. So what is NIPAM? So NIPAM is short for N-Isopropylacrylamide, and it's the main monomer that is used to measure dose from high-energy X-rays, and it does this through free radical polymerization. So what it does is that when you have X-rays that come through, you've got an X-ray that strikes the double bond, it creates a radical or a single electron, which is very, very unstable, and then it forms single bonds by combining all the little individual monomer chains together to form a poly-NIPAM. And next is BIS. So BIS is short for NN, Methylenebisacrylamide, and it's a cross-linker which connects 2 different polymer chains together that increases the viscosity and the light attenuation when you, after being irradiated. And it does this by connecting the 2 double bonds at the end over here. Another bit that we need to add in to gel dosimeter is an antioxidant to get rid of all the oxygen, because oxygen is an inhibitor and it stops the polymerization process, making the dose less sensitive. So we want to get rid of that. And this thing, so THCP, which is short for tetrakis hydroxymethylphosphodium chloride, and its main role is an oxygen scavenger. And what is really good about it is that it gets rid of all the oxygen, but it doesn't react with the monomers, which is what we want. And so say that we made our gel, and we made it under normal temperature, normal standard temperature and pressure, so there's going to be some oxygen when we're making it. We add some TPHC, and then the oxygen is scavenged, and it's free to use, so it's good to go. And so after we radiate it, you get some bonds that are formed between the NIPAM and the BIS, which connects the NIPAMs together. And then what you should get in the end is a very, very nice gradient, but in 3 dimensions instead of 2. So the main significance and benefits is that you can, so it's very good for treatment planning verification. So for CyberKnife, IMRT, and VMAT. Because there's limited work at the moment at St. Charles Gardner Hospital, it can be used to assist with other projects. So for example, for Tanisha's project, so the main problem with using film is that you can't really use it on contours because it will break. So if you 3D print a mold and then add gel to it, then you can measure the surface dose. For the case of Rachel's project, you've got the or she's 3D printing, say, a pelvis, so you can fill it with gel and simulate the air cavity. And because it's tissue equivalent, you can see after irradiation the dose to the normal tissue that's happening around it. So because it's in 3D, it's great. But for future research, it could be used for internal dosimetry, for radiopharmaceuticals, or it can be used for proton therapy to measure the Bragg peak. So here's the project timeline. So it's basically split up into 5 sections called the fabrication, the calibration, the examination, the verification, and then the publication that comes at the end. So I'll go into these in a little bit more detail. The first 3 stages will take the most longest. That's me making the gel and testing it out and calibrating it. And the last 2 bits will take about 2 to 3 months, which is comparing to a TPS system and then finishing it off. So here's just another breakdown. So the fabrication deals with all the chemicals making the gel. The calibration is just irradiating the gel, calibrating it, and make sure we have dose linearity. The third bit is the testing. So we ensure that it is temporally stable. It's fine with steep dose gradients. There's little temperature dependency and dose rate dependency. And then after the examination bit, we'll be trialing it against a TPS system and then testing the congruency using a 3D gamma map. And after that, we write the thesis. Or I will, not you. So the main fabrication bit, so this is a bit of a mouthful, but in short, you get some gelatin, you put in some water, you heat it up, you add bis, and then after that's dissolved, you add the NIPAM, and then you add the antioxidant. And then you put it into plastic test tubes, and you just leave it there for 24 hours until it sets in the fridge. So this was basically created by Senden and others in 2006. And so the way that my project is going to add to it is that it's going to iterate the different combinations between the BIS and the NIPAM, because there is inconsistency, and see how the gel responds. And so Senden did his results with 3 parts, or 3% NIPAM and 3% BIS, but some people like Hisaya did other proportions and found different results. So there is still a bit of inconsistency, and so my project is going to add by filling in this table. So the next bit is the calibration. So after irradiating, you can image it using MRI, which is linear up to 26th grade, or you can use CT, optical or X-rays, and that's linear about 10. And so as you can see here in figure 2 with the relaxation rate, so they use T2 weighting of relaxation rate against dose, you can see that it's pretty linear up to 25, 26 gray, and then it plateaus. For CT, the same thing happens for up to 10 gray and then plateaus. And then in figure 2, you can see on the axial, sagittal, and coronal planes that the higher the dose, the more darker the patches are. So that's great. You can see in 3D, and you can extrapolate it when you get lots of slices. It's great. So in terms of examination, we're going to test for its temporal stability. So the NIPAM gels that have tested just thus far said that it is stable past 24 hours and up to 360 hours. And they did a gamma map analysis against a TPS, and it's 97% past 24 hours to up to 360 hours. The reason why that it breaks down after 360 hours is because it starts to react with the ambient oxygen and it stuffs it up a little bit. And before 24 hours, it's because it's still polymerizing. So you need to let it set for 24 hours. So you can see with the time on the x-axis and the pass rate on the y-axis, it's pretty, it rises up, maintains at around 97%, and then drops back down. For dose gradient dependency, this is more not appropriate. This is more applies to a stereotactic surgery where you really, really want steep dose gradients to not irradiate the normal tissue surrounding it. So if you look on this diagram here, where if you go from top left to bottom right, you've got an increased collimation sizes with between 4, 8, 14, and 18. And they tested the dose of the gel with the black dots and the solid line against the TPS. And you can see there's like a fair bit of congruency between them, which is great, except in the lower dose regions and towards the plateau. And this was assessed against a gamma plan TPS, and the mean dose was around 5.5%, plus or minus 1, plus or minus 2 for dose. So for here, they tested the profile on the x-coordinate at the maximum depth dose, and and then normalize the dose, or the maximum dose, on the y-axis. For scanning temperature dependency, we can see that the gel is quite sensitive to temperature, but only when you scan it. It's not when you're irradiating it. And so this is more pronounced in MRI than it is with CT, because MRI takes half an hour to make an image compared to CT, which takes a good quick 6 minutes. So when you have an increase in temperature, there is a decrease in signal. And yeah, as you can see on this graph here, I think it was measured at 22 degrees, which is the full bit, the solid line, and 27 degrees, which is the empty line. So you can see that there's still dose linearity, but there is much less of a signal. So when I'm imaging it using MRI, it needs to be in a temperature-controlled environment. And for dose rate dependency, there's minimal effect on dose rate. So long as it's the same dose rate throughout the whole thing, it's fine. It maintains dose linearity. And so when I'm measuring, I'll be keeping something consistent like the field size of the LINAC, where the gel is located at the radiation isocenter, and the beam profile. And so our last step is to compare with a treatment planning system. And the good thing about a treatment planning system is that it does all its calculations on dose or tissue equivalency. And the thing about gel is that it is tissue equivalency, and we've proven it here. So with this graph with part A and part B, so this is the axial, sagittal, and coronal planes that they're measured using an NIPAM gel. And that's the gamma index. So gamma index is just basically how well one bit of dose matches to the TPS, and see how well they match up. And so you try to make sure that the gamma index is less than 1. But what's more important is the failed maps. So if there's large differences between the treatment planning system and the gel, then there will be a lot of failed maps, but we can see there's basically none. So that tells me that the gel that I've created is tissue equivalent, and therefore there is no or little corrections that are needed on the TPS, which is fantastic. And so this was tested using Eclipse TPS using a Monte Carlo system. And I'll be doing this using a gamma map analysis. And the last bit is just publication, which is me writing until, lots of coffee. So here's my literature review of most of the people who contributed between the chemical composition, imaging techniques, dose response, and spatial distribution, and the treatment planning system. Any questions? Yes? Dose measurement. So if you're level of accuracy, so if you're doing a gamma map analysis, the dimensions I'll be doing is, it's 2%. I'll be using this accuracy, so it's 2% per 2 millimeter criteria against the treatment planning system, and we expect to be about 97%. So make sure it's congruent with all the other literature, or better. Sorry?
Does it depend on where you're measuring which organ?
Where measuring?
Like for which organ? Different treatments can be.
I think it's independent. Independent, yeah. And if need be, I can look up the density of the organ and then adjust it on the on the gel. So when I'm making it up, so if I'm making it more dense, I'll just add more gelatin to it. Should be great. Yes.
Are there any plans on where it's going to be?
So MRI and CT, do you have any plan for access to MRI?
Yeah, so we've got some good news. So quite recently, we've got some recent graduates or alumni who are willing to will lend some time of their MRI or research MRI, which should be good just for this, which uses MRI. And for CT, hopefully we can get some access to the CT. Yeah.
And then one of the problems with gels is like differences between different batches.
Yes.
So you're going to do that kind of investigation.
Sorry?
Independence of making batches.
Yes.
So batches may be slightly different in their response.
Yes.
To make multiple.
Yeah, so I'll be making multiple batches. So when I'm calibrating it, I'll be using the same batch. Yeah, because it all depends on the conditions. And if you mix it just slightly differently, you can change the oxygen levels and all that. So I'll be using the same batch for calibration and testing. Yeah.
It's exactly like film dosimetry we need to use calibration for.
Yes. Yeah.
Any other questions, Martin?
So for your gel,
Mhm.
does it specifically replicate the tissue equivalency for density, water content, or any other?
So, luckily, I've got a... Don't mind that. So... Actually, no, this question will do. So basically, so what was your question? Sorry, it was...
Does it replicate what specifically properties of tissue does it replicate? Like if you just mentioned that is equivalent.
Yes.
So is it equivalent in water content? Equivalent in?
So what the test is equivalent in electron density, specific gravity, mass attenuation, and the way that light interacts with it.
So
Optical properties. Yeah. Sorry. Yeah.
Okay.
Yeah.
Are either of these BIS or not NIPAM, NIPAM?
Yeah.
Are either of them toxic? Are they?
Yes. So basically, what's good about NIPAM is that, and this also applies to BIS as well, is that it is considered a non-toxic. Well, it is considered a normal toxic or non-toxic monomer. And the thing is that, you do your normal chemical stuff. It's like don't eat it and like don't rub your eyes with it. But other than that, what has been found when I looked up the material safety data sheets or the MSDS sheets is that you can pour it down the sink or you can put it in the trash and it's completely safe. New research was in the, not new, 2006. It was for, they were looking for new ways to make gel non-toxic because it used to be made of acrylamide, which was a neurotoxin. And there's a story about 50 people in Norway when they were mining and they found acrylamide in the ground, they died due to overexposure of acrylamide. You lose sensation in your hands and feet and then eventually your heart. So yeah, so they're looking for, they found new ways and they found NIPAM to be non-toxic.
When you look at I think you mentioned this, but I may have missed it. When you look at the different mix of the BIS and the
Yes.
NIPAM, what are you optimizing? Is it linearity? Is it sensitivity? Is it the saturation dose? What are the things?
So what I'm looking for is that I'm mainly optimizing the sensitivity of it. So what I'm expecting is that the more NIPAM, the more BIS that I add, the more sensitive there is because there's more monomers for it to react. That's what I'm sort of looking for. But the main aim of the project is to have a look at the trends to see if you change the NIPAM composition or you change the BIS composition, what happens. Yeah.
Any other questions? Thanks very much.
Cool.